So in this video, we're going to review how we would calculate the pH of a salt solution. So remember, salt is an ionic compound. So let's go ahead and pick on an ionic compound, so something like sodium nitrite, NaNO2. And we can go ahead and we can look at this and say, well, the sodium ion, that's coming from a strong base, so that means it's going to be neutral. The nitrite ion, it's not coming from a strong acid, right? We don't remember that being on the strong acid list. Therefore, it's going to be basic. And since the sodium is neutral, we can basically ignore any reaction the sodium undergoes in solution. Instead, we just have to focus in on the nitrate ion. And remember, because it's a base, we are going to want to write the Kb reaction. So let's go ahead and write out the Kb reaction. So we can ignore the sodium, and we can just focus in on the base. The Kb reaction is where it reacts with water. And if you remember, right, the base is acting like a base because it's capable of accepting a proton from water. So that's going to turn it into nitrous acid. And let's see, water is going to lose a proton, so it's going to be the hydroxide ion. Of course, that is what makes it a base, right? So remember, Arrhenius said bases are things that increase the hydroxide concentration. Now, we meet our friend the ice chart. Told you we're going to love ice charts in this course. So we can use molarity, we can use pressures, we can use moles. Really no reason to use pressure in this problem. Moles we could. I mean, we're not told we have a liter of solution or anything, so we probably really can't calculate moles. But later on with buffers, we'll see that moles give us an advantage. Pure liquids don't enter into the equilibrium constant expression, so we could ignore them. We don't have any HNO2, right? We're not told in the problem we have any. The hydroxide ion in pure water is about 10 to the minus 7. So we're going to go ahead and we're going to assume in this problem here we're at 25 degrees C. And we're going to assume that the original concentration of hydroxide in water is so small we can ignore it. So then we fill out the change line. So we know it goes from left to right because that's the only way it can proceed without generating a negative concentration somewhere. So minus x plus x plus x. And at equilibrium, we just essentially sum together the initial and the change. And I'm going to drop the units because in equilibrium constants, we never write the units for concentrations in. So Kb is equal to the concentration of products over reactants at equilibrium. Okay, and that's given by the bottom line values on the ice chart. So we got it x times another x, well that's x squared, divided by the nitrite concentration. Well, 0.1 is where it started, x is what it went down by. And the thing is, right, if we had a number for Kb, we could solve, but we don't have a number. We've got two unknowns here. So we can't really solve the bottom line of the ice chart, and we can't really solve for the pH. So what is the solution? So here's the solution to the problem here. So we want to know Kb for the nitrite ion, and we probably won't find Kb for the nitrite ion. So that puts us in a bit of a pickle. So how do we figure out Kb if it's not something we can look up? Well, it turns out that there's a really cool trick here. And let me take a weak acid and let me take its conjugate base. So remember, the conjugate base is just the same thing minus a proton. And let me write out the Ka and the Kb reaction. So Ka for my weak acid is essentially the reaction where Ha reacts with water and it forms the hydronium ion and the counter ion A minus. And Kb for that weak base, right, that conjugate base, the counter ion, is the reaction where A minus reacts with water and it takes a proton from water and it, in this case, reforms that weak acid and it forms the OH minus ion. And remember, the thing with these equilibrium reactions is that we can sum them together. And if we sum them together, we multiply the equilibrium constants. So Ka for the acid times by Kb for the conjugate base, okay, is the new equilibrium constant. And if we add together the equilibrium reactions, actually, I'm going to do this a little bit sloppily here. I'm not going to actually write them out yet. I'm going to pre-cancel. I've got Ha on the left and the right, and I got A minus on the left and the right. And so you can see my actual reaction is water in equilibrium with the hydronium and the hydroxide ion. And you might remember that's the Kw reaction. So that means that all this thing here is equal to is Kw. So that gives us a really awesome expression. So Ka for the acid times Kb for the base, that's for the conjugate pair, is equal to Kw. So if we want to find Kb for the nitrite ion, all we got to do is rearrange this equation, right? And we could rearrange and show it's equal to Kw over Ka. So if we want this for nitrite, then all we got to do is look up Ka for nitrous acid and divide it into Kw. And if you remember, Kw, right, is 1 times 10 to the minus 14 at 25 degrees Celsius.